You've probably heard these names for the activation of neural networks. ReLU, GELU, Sigmoid, or this kind of names. But what are those? Before we go through the activation function, it's necessary to know why do we even need them. To model complex relationships, the network needs something between those layers that bends and reshapes the signal. That's the job of an activation function to address that. But what happens if we remove them completely? Removing the activation functions from a neural network, for example with 100 layers, can collapse the entire network into one equivalent linear or affine transformation. So stacking more layers is not enough. And we need this nonlinear variable in those neural networks to make sure that they address nonlinear problems. But neural networks have repeatedly changed which activation functions they use. They move from sigmoid to tangent hyperbolic, to ReLU, then GELU, then SiLU. And many modern language models now use SwiGLU. Why did every generation need a different solution? It started with Sigmoid. As you can see the equation in the screen. Sigmoid compresses every input into a value between 0 and 1. A very negative input becomes close to 0. A very positive input becomes close to 1. That makes Sigmoid useful as a smooth gate, which is why it still appears inside architectures such as LSTMs or long short-term memory. But it has a serious weakness. At both ends of the curve, sigmoid becomes almost flat. A flat curve has a derivative close to 0. During backpropagation, multiplying many small gradients together can make them shrink until earlier layers barely even learn. This is the vanishing gradient problem. Tangent hyperbolic improve one part of sigmoid. Unlike sigmoid, tangent hyperbolic is centered around 0. Negative inputs produce negative outputs, while positive inputs produce positive outputs. That can make optimization easier, but tangent hyperbolic still becomes flat for large positive and negative values. Its gradients can still vanish. Deep neural networks needed something simpler. That led them to ReLU. ReLU follows one hard rule. Negative values become 0. Positive values pass through unchecked. ReLU is really cheap to compute and it's much easier to use in deep networks. On its positive side, its derivative stays at 1. So the gradient does not gradually disappear simply because the input becomes large. But ReLU introduced a new problem. If a neural network repeatedly receives negative inputs, its output and gradient can remain 0. The neuron may stop learning completely. This is the dying ReLU problem. ReLU also makes a very harsh decision. An input of positive 0.01 survives. An input of negative 0.01 disappears. Researchers began looking for smoother alternatives. One of them was GELU. GELU does not apply a hard cutoff. Instead, it smoothly weights each value using the cumulative distribution of a normal distribution. The intuition is simple. ReLU asks, is this value positive or negative? GELU asks, how strongly should this value pass? A small negative values are reduced rather than immediately erased. Large positive values pass through almost unchecked. This smooth behavior worked especially well in transformer models. Another smooth activation is SiLU, also known as swish when used in its standard form. It's simple, it's x multiplied by sigmoid of x. SiLU is self-gating. The input provides both information and the signal that decides how strongly that information should pass. So GELU and SiLU solve a similar problem. They replace ReLU's hard boundary with a smooth transition. Modern LLMs then took the idea further. Instead of transforming one stream of values, they create two learner streams. This is the idea behind SwiGLU. One path creates candidate information. The other creates a gate. The model is no longer applying one fixed rule like remove every negative value. Instead, it produces different gates for every input token and hidden feature using learned projections. One path says, here is the information I could send forward. The other says, here's how much of each part is useful right now. This flexibility is one reason SwiGLU has become common in modern language models. But it's not free. SwiGLU needs extra linear projections, which means more parameters and computation than a simple ReLU layer. To compensate, model designers often reduce the intermediate hidden dimension. So the evolution of activation function is really the story of solving different bottlenecks. Inside a transformer, these functions usually operate in feed-forward network. Attention, let's tokens exchange information. The feed-forward network transforms that information and the activation determines how the signal is reshaped before reaching the next layer. That small mathematical choice is repeated for every token across every layer. So Activation functions influence training stability, computation, and final model quality. And what about Softmax? Softmax is often called an activation function, but it solves a different problem. ReLU, GELU, SiLU, or SwiGLU transform hidden signals. Softmax takes the group of scores and turn them into normalized weights or probabilities. This is how attention scores become attention weights, and how output logits become next token probabilities. And let's explore Softmax in the next video. It's enough for now. Until the next video, good morning, good afternoon, and good evening. Bye.